Hello everyone, welcome back to another session for thermodynamics subject. In this session, we are going to continue our discussion about the control volume or open system. In previous session, actually, in the global classroom, you have learned already about the uh, different types of open system, and you have learned how to deal with the problem created for the steady state, especially steady state control volume. And also in previous session, we had different examples to see how you can calculate the mass flow rate, volume flow rate, or even the energy changes in those control systems. All of those information are just the basic and fundamentals to deal with the real engineering problems. And generally, for engineering devices, for many of the engineering devices, we can assume that we have a steady state flow or a steady flow actually uh, in those devices like different kind of turbine nozzles and other engineering devices. We can assume that we have a steady flow in those devices. And in this session and also next session, we will discuss about some of these engineering devices which we have a steady flow in those devices, and we'll use the uh, equations and energy balance, mass balance definitions for these type of devices, and we will calculate the energy changes and energy or energy required for these devices by the assumption of having a steady flow in these devices. These devices are like turbine, compressor, heat exchangers, and pumps, and this steady flow assumption actually it is a reasonable assumption because usually these devices are working non-stop for months before we shut down these devices for maintenance, and just during that before and after that shutdown may we don't have this steady flow, but during their operating uh, uh, mm, period, we have a steady flow in these devices. So let's see how we can use the uh, our equations, our knowledge to solve problem related for different devices, engineering devices actually, with a steady flow in them. The first uh, engineering devices which we can assume to have a steady flow in them are nozzles and diffusers. Nozzles and diffusers are commonly utilized in different equipment, different engineering equipment actually, like jet engines, rockets, spacecraft, and even garden houses, as we also seen previous examples, but we didn't discuss about the nozzles. But here we will see how we can calculate the change in the energy in these devices. A nozzle is something like this, device like this, which its diameter is changing. If we just this is a 2D illustration of a nozzle. A nozzle is actually a 3D uh, uh, object like what you can see here. Its diameter, its input diameter is higher than its output diameter. So this is a shape, a general shape for a nozzle, and for a diffuser, the general shape is like this, which its entrance diameter is uh, uh, smaller than the output diameters. And due to the change in the diameters of the nozzle and diffusers, the pressure and volume also will be different. The flow will come to the nozzle from this side, which we have bigger diameters. Then the velocity of the flow after nozzle, at the exit of the nozzle, will be higher than the entrance velocity. And this is and in other side we have opposite behavior for the diffuser. The velocity of the flow to the diffuser at the entrance is higher than the velocity of the fluid or flow after diffuser. And these changes is not only for the pressure and for the velocity, also the pressure of the fluid will be different, or of the flow. The In nozzle, velocity is increased, but pressure will reduce. In other words, if we write like this, P1 and P2 will be less than uh, P1. And for diffuser is we have an opposite behavior. Then if we have P1 in the entrance of the diffuser and P2 at the output of diffuser, pressure will be higher for a diffuser. So we have these shapes actually, and we use diffuser and nozzle to change the velocity and pressure of the flow according to our requirement. For example, for a rocket, we are interested to increase the pressure to provide that force for moving of the rocket. So usually we use a diffuser. Then the pressure at the back of the diffuser will be higher than the pressure at the input of the diffuser. And this difference in the pressure, P2 minus P1, it's the total pressure, or delta P, will cause a force on the diffuser, and it will go forward. This is the reason for the movement of the rocket, and because of that we use this equipment or this device for the diffuser. So a nozzle is a device that increases the velocity of fluid at expense of pressure. Pressure is reduced. A diffuser is a device that increases the pressure of a fluid by slowing it down. So velocity is reduced by pressure is increased. And as you can see here, the how is the shape, the cross-section area. This is important according to the shape. Also, you can guess if we have nozzle or we have a diffuser. And this shape actually, for nozzle and diffuser, is different according to the velocity of the flow. If we have a subsonic flow, subsonic means the velocity of the uh, flow is less than velocity of the sound. Velocity of the sound in air actually is 300 something. So if the velocity is less than that, we have a subsonic flow. And if the velocity of our flow in the nozzle or the is higher than the velocity of the sound, then we have a hypersonic flow actually, or supersonic flow. For a subsonic flow, the shape of nozzle and diffuser is like this. And for a supersonic flow, the shape will be different and will change. And actually, for supersonic, the entrance of the nozzle, the cross-sectional area of the entrance of the nozzle is less than its exit. So we will have a contrast in the shape of the nozzle and diffuser for subsonic and for supersonic flow. So the shape of nozzle depends on the velocity of the flow as well. But generally, what we are dealing with is usually subsonic flow in many of the industrial devices. However, if we have supersonic, the calculation and so on will be same. The only difference is in their shape and In that case, for supersonic, this one will be diffuser, this one will be nozzle. And for if we want to find energy balance for this control volume in nozzle and diffuser, we have flow to the nozzle, then go the flow from the nozzle. Then we can select the flow, the fluid or the inside the nozzle or diffuser as our control volume. Then we can calculate and we can write this energy balance for the our control volume. As you can see here, generally in nozzle and diffuser, we don't have any change in the our uh, flow is a steady flow as we discussed earlier. Then we don't have any change in the mass or uh, um, mass of the control volume uh, will be zero or change in the mass of control volume. Then it will be very easy to deal with these problems and find the energy balance equation for these equipments. For these devices, generally heat transfer is zero because usually the speed of the flow is very high and the time which we have that specific part of the flow inside the nozzle is very limited and we don't have enough time to have a heat transfer between the uh, substance in our control volume and surrounding. So generally it is assumed that the heat transfer from for the control volume in the nozzle and diffuser is zero. And also we don't have any kind of the work generally for nozzle and diffuser. We have for our control volume and changes in delta P or potential energy in nozzle and diffuser for our control volume is can be also neglected for potential energy. But because uh, the velocity of the flow in the nozzle and diffuser is usually very high, we generally we cannot ignore or neglect the uh, kinetic energy, the change in the kinetic energy of the flow at the entrance of the nozzle or diffuser and the exit of that nozzle or diffuser. In other words, we may have a significant change in the kinetic energy of the flow in our control volume. It depends on the problem and we need to compare the change in the kinetic energy of the flow in our control volume with other changes of the energy which is related to change in the internal energy of the flow actually. So we can write the energy balance like this: E dot in equal to E dot out for a nozzle or diffuser, and E dot in what we have is M dot times H1. This is so we have change in the enthalpy. We have change in the enthalpy of the flow in nozzle or diffuser, and M dot we power to divided by 2 is the kinetic energy. This term is related to the kinetic energy of the flow at the entrance of the nozzle or diffuser, and it that out at the output of the nozzle or diffuser. Again, we can write like this, which is the enthalpy and kinetic energy. So we can see here we have neglected Q or Q dot or heat transfer. We don't have any work in nozzle and diffuser, and also we have neglected the change in the potential energy in the nozzle and diffuser. Then in an example, we will see how we can use this equation to find the change or to find pressure, velocity, and other properties for the working fluid in the nozzle or diffuser. Here we have an example which is related to the diffuser. As I discussed earlier, for diffuser, we will deaccelerate or decelerate the velocity of the flow actually, or we reduce the velocity of the flow, and we will increase the pressure of the flow. And as I discussed earlier, we have these kind of devices in jet engine, for example, like what you can see here. And we have entrances in the flow is in this direction. The air will come to this uh, jet engine and will go out from this side. So you can see here the shape is like this actually. And as I discussed earlier, this is a diffuser. The pressure here will be higher, P1, P2, higher than P1. Then it will force the jet engine or the airplane actually forward. So this is the reason why we use this shape for jet engine. What we have here is a jet engine. The air come to this engine, which is a diffuser actually, with temperature of 10 degrees Celsius, and its pressure is 80 kilopascal. And it is we have a steady flow, as it is mentioned. Steadily, we have a steadily flow, and its velocity is 200 meter per second. So the velocity at the entrance or V1 is 200 meter per second. The pressure or P1 is 80 kilopascal, and temperature or T1 is 10 degrees Celsius. This is at the input of this diffuser. And the inlet area of the diffuser is also mentioned. The cross-sectional area of that A1 is 0.4 meter square. The air leaves the diffuser with a velocity that is very small compared with the inlet velocity. So at the output, V2 can be neglected actually compared to the V1, so we can assume it is 0. Then we need to determine the mass flow rate of the air, or m dot, in our control volume actually. The temperature of the air leaving the diffuser, T2 also. So we need to find m dot and also T2 for our diffuser. Let's see what should be our assumption. As I said here and earlier, we can assume that we have a steady flow in nozzle or diffuser. And as mentioned here also, we can assume that we have a steady flow process here. Then we don't have any change in with time at any point in our control volume. If we select the control volume as I shown here, then we don't have any change in the mass of control volume, or delta MCV will be 0, and we don't have any changes in energy, total energy of our control volume, or delta ECV equal to 0. This means E in is equal to E out, or even E dot in is equal to E dot out. This is according to our first assumption, which we have a steady flow, which is discussed earlier. And assumption number 2, air is an ideal gas since it is a high temperature and low pressure relative to its critical point values. I have already discussed in a few examples that we can assume that we have a ideal gas if the properties of that gas is uh, enough far from the properties of that substance in critical point. So we need to compare our pressure, temperature, and the other properties of the gas, which is air here, with the critical values uh, for these properties of the air in the critical point. And if we do that, we will understand that the air which we have here is an ideal gas. So we can use that ideal gas relation. And assumption number three, the potential energy changes is zero. This is our assumption. And also, it is mentioned that, and also here is not mentioned any information about the change in the elevation or change in the velocity of the change in the potential energy. So we can have this assumption. And assumption number four is heat transfer is negligible. It is not mentioned anything about that. Then we can have this assumption that we have good insulation and also the time which the flow is in our control volume is very small, so we don't have any heat transfer for the fluid when it is in our control volume, which is the diffuser. And assumption number five is the kinetic energy at the diffuser exit is negligible. Why? Because it was mentioned that the uh, velocity at the exit is very small compared to the velocity of the air at the entrance of the diffuser. And also, assumption number six, there are no work interactions, which simply you know why, because we don't have any uh, uh, change in the volume, and also we don't have any type of work in a diffuser or in a nozzle generally. So as I discussed earlier, we need to first select our system diffuser. We select diffuser as our system, something like this. Then this is a control volume because we have mass crosses boundary of our system. So this is obvious as you have learned from the beginning of this chapter because we have mass transfer from our control volume. We have flow. The air come to our control volume from this side and will go out from this side. So we have a crossing of the mass of the substance from the boundary of our system. So we have a control volume or open system actually. So and also we know that we don't have any leakage actually of the mass from the uh, boundary of the our system except the entrance and output. So all of the mass of the flow which come to our control volume actually, all of the mass which come to our control volume will go out from our control volume. Not any waste of the mass in our control volume. So m dot 1 is equal to m dot 2. M dot 1 means mass flow rate to this control volume. M dot 2 is the mass flow rate from the or out of the control volume, which are equal. M dot 1 is equal to m dot 2 equal to m dot general. Then to determine the mass flow rate initially, we need to use that ideal gas relation actually. V1, which is the specific value, V1 equal to R T1 divided by P1. You know this equation is ideal gas relation, which we have already discussed. So R for air from table which we had earlier. We have discussed in chapter 3. From the table for ideal gases, if you go to that table, you can find ideal gas constant for air, which is 0.287 kilopascal meter cubed per kilogram Kelvin, and T1, the initial temperature, which was mentioned 10 degrees Celsius, we need to convert to Kelvin. 10 plus 273 will be equal to 183 Kelvin divided by P1, which was mentioned 80 kilopascal. Then if we solve this, do this calculation, we will find the specific volume of the air at the entrance of the diffuser, which is 1.015 meter cube per kilogram. This is the specific volume of the air at the entrance of the diffuser. Then m dot will be equal to this, m dot equal to 1 divided by V1, V1 specific volume. This V, capital V, is velocity of the air at the entrance, velocity, and this one is a specific volume, and this one is cross-section area of the diffuser at the cross-section area of the entrance of the diffuser. And you know this equation, actually this equation is this one, maybe you remember this like this, MVA, M dot equal to rho VA, rho density, V is the velocity of the flow, A is the cross-section area of the which flow is flowing through that. And as I discussed earlier, rho and specific volume or density and specific volume are like this. Rho is divided by 1 divided by V. So we can have this, we have this equation m dot equal to 1 divided by V1 times capital V1 times A1. This one, we just substitute this specific volume which we have calculated. The velocity of air at the entrance of the diffuser we have 200 meters per second, and cross-section area of the diffuser at the entrance is also given, which is 0.4 meter squared. Then we can calculate the mass flow rate from this diffuser. According, as I discussed earlier, this m dot or mass flow rate is the mass flow rate through our control volume at the entrance, at the exit, and at each cross-section area of the diffuser actually, because we don't have any other mass to the system or from the system, from other boundary of the system, only from entrance go to the output of the diffuser. Then m dot will be 78.8 kilogram per second. This is mass flow rate. And to find the uh, uh, actually part B, which was the temperature of the air leaving the diffuser, or T2, we can start by writing the energy balance for our diffuser. If you remember, the energy balance, the general equation is like this: E dot in minus E dot out. Total energy come to the system minus total energy which go out from the system, which is the control volume here, which is diffuser here, is equal to change in the system with time. dE of the system, change in the energy of the system per time. Here what we have is steady flow. And for a steady flow means we don't have any change in the energy of the system or our control volume for time. Then we have this will be equal to 0. Or E dot in minus E dot out will be equal to 0, or E dot in equal to will be equal to E dot out, or energy rate to the system is equal to energy rate from the system. And as you have seen this equation in previous slides as well, the energy which come to the system are which we have for the control volume at the entrance of the diffuser are enthalpy of that diffuser, which if you remember we had this, it means at the entrance of diffuser we have flow energy, which is PV, actually pressure and volume of that, and U or energy, internal energy. And as you remember, we use enthalpy instead of these two for simplification. Actually, the reason to define enthalpy is generally for this purpose, to have a more simple properties, which is combination of the PV work or PV energy and internal energy. So we have that enthalpy and also kinetic energy, because we have a flowing fluid actually, so it has some kind of energy. It has velocity, so it has kinetic energy. So we can write like this: m dot times h1 plus v1 power 2 divided by 2, E in energy at the entrance of the diffuser, and the output of the or in exit of the diffuser, we have m dot times h2 or enthalpy of the fluid at the exit of the diffuser, plus v, which v2 power 2, which v2 here is the velocity at the exit of the diffuser divided by 2. We can write this equation because for E dot in or E dot out, we don't have any heat transfer to the system or from the system. Or we, at least we had assumed that we don't have any heat transfer to the control volume or from the control volume. So Q dot equal to 0, no work rate, and also we assume that potential change in the potential energy of the flow in the diffuser is 0. We can have all of these. All of these are according to our assumption. So we have only enthalpy and kinetic energy at the entrance and at the output of the diffuser. And by simplification, by canceling m dot from both sides of this equation, and by if we bring this part to the left side and write according to the H2 or enthalpy at the exit of the diffuser, we will have this equation: H2 equal to H1 minus V2 power 2 minus V1 power 2 divided by 2, which V2 is the velocity of the air at the exit of the diffuser. But as we discussed earlier, the velocity, and it was mentioned in the question instruction, V2 or the velocity of the air at the exit of diffuser is much lower than velocity at the entrance. In other words, we can ignore this V2. So we can also remove this V2 in our equation, and we will have just this H2 equal to H1 minus, or actually here plus V1 power 2 divided by 2, or we can just put 0 here instead of this, then do the calculation. But first we need to find H1. To find H1 we need to go to the table to find H1, which is enthalpy for air in this temperature. As it is mentioned, we know how much is the temperature of the air at the entrance, so we need to go to the table for the air, which is table A17 for this temperature. Okay, this is table A70, ideal gas properties of air. Our temperature is 283. We was in this range. We have temperature 280, we have temperature 285, and we have enthalpies for air in this temperature, but our temperature is here 283 Kelvin actually. So what we need to do is to do interpolation to find this enthalpy. And if we do interpolation, and also you can see here For this temperature, 280 Kelvin, H is, or enthalpy is 280.13. For this temperature, 285, enthalpy is 285.14. Then the enthalpy for air in this temperature also should be between these two. So the enthalpy for that temperature by interpolation, or simply by just by just simply by these reasons, which we should be between these 280 13, 285 14, you can see here 200, 200, 285, 285. Even without interpolation, you can guess that 280 degree, 83 Kelvin. Then the temperature also, the enthalpy also will be 283 something, which according to interpolation, it is 283.14. I do not go to that interpolation, which is obvious, and we had many examples for that in previous examples. So by interpolation, you can find H1 as well in the table A17. By substitution of this H1 in this equation, we have velocity at the entrance of the turbine as well. We can find enthalpy, or H2, at the exit of the this diffuser. So we have H2 as well, but what we are looking for is temperature. So we have H2. Let's go to the our table A17 again. The temperature, the enthalpy which we found is 303. So 303, we have 300 here and 305 here. So temperature, the enthalpy is between these two values. Then temperature is between these. So what we have here, temperature, enthalpy. Temperature, we have 300. Our temperature, we don't know how much is it, and 305 Kelvin, and enthalpy which we have 300.19, the enthalpy which we had calculated here 303.14, and for this temperature enthalpy is 305.22. So this is just a simple interpolation problem. If we do this interpolation to find T2, T2 will be 303 Kelvin. Then we can find the temperature of the air at the exit of the diffuser by this interpolation. So temperature of the air will be 303 Kelvin at the exit of the diffuser, which was for the jet engine. Here we have another example. However, it is in the English unit, but it is about nozzle. As I said earlier, we have acceleration of the flow actually in the nozzle. So here what we have is acceleration of steam in a nozzle. Our nozzle is like what you can see in this figure, a steam with 250 psi pressure and 700 Fahrenheit temperature steadily. This is important. Then we can understand that we have a steady flow in our nozzle. The steam with this pressure and temperature enters in a nozzle whose inlet area is zero point 0.2 squared feet, as it is also shown here, P1, T1, and A1 for our nozzle. The mass flow rate of the steam through the nozzle is also given, which is 10 point per second. So we have m dot as well. And this steam leaves the nozzle at 200 psi pressure with a velocity of 900 feet per second, and it is shown here as well. So we know how much is the pressure and the velocity at the exit of our nozzle. And as you can see here, initial pressure is 250 at the entrance, at the exit is 200 psi, and you can see the pressure is decreased, and velocity, we don't know how much is the velocity at the entrance, but at the exit is 900 feet per second. But we can guess that in a nozzle, generally pressure is decreased and velocity is increased. So V1 will be less than V2. And we don't know how much is the V1, and we will calculate actually. And for this nozzle also, we have heat loss from the nozzle per unit mass of the steam, which is 1 BTU per pound. Uh, as we discussed earlier, generally we assume that we don't have any heat transfer for the flow in nozzle or diffuser. But here it is mentioned that because of the uh, maybe high temperature of the flow or the low velocity of the flow in our in the nozzle, we have a small heat transfer which is equal to this, which this heat transfer is from the steam in our control volume to the surrounding, which is equal to 1.2 BTU per pound. So here we have also heat transfer, and we need to notice to this in our calculations. In part A of the question, we need to find the inlet velocity, as I said, V1, and also we need to find the exit temperature of the steam or T2. This is information which we have, and what we are looking for are V1 and T2. Let's see, first of all, what should be our assumption or for this problem. We have a steady flow process, then delta MCV and delta ECV, or change in the mass of the control volume is zero, and also change in the energy of the control volume is zero because we have a steady flow. And there are no work interactions. The other assumption, which is obvious. And assumption number 3, the potential energy changes is zero. Delta PE is zero because the flow comes here, goes out, no change in the elevation. As you know, the change in the elevation is only due to the change in the uh, elevation, or if it was like this and we have H, then we can discuss about the change of the potential energy. But here generally we can assume that delta P E is equal to 0. So what we have here actually is uh, kinetic energy, internal energy, uh, and also the PV or flow energy, which can combine the enthalpy and defining that enthalpy, and also we have heat transfer. Later we will discuss about that. Moreover, what we have here is uh, the selection of control volume. Generally, for nozzle, like what we had for diffuser, we select our control volume like this, the dashed line you can see in this figure, and flow come from this side to the nozzle, goes out from this side, and as you can see, the entrance, the diameter or cross section area bigger than the cross section area of the exit of the nozzle. But on the whole mass flow rate to the nozzle is equal to the mass flow rate from the nozzle, or m dot 1 at the entrance. Mass flow rate at the entrance is equal to mass flow rate at the exit of the nozzle. So we have m dot 1 equal to m dot 2 equal to m dot. And as you notice here, we have a control volume. Our system is control volume because mass is transferred across the boundary of our system. So it is the control volume. First of all, let's find the properties for the substance, which is steam or water vapor at the entrance of the nozzle. What we have for steam at the entrance of the nozzle is its pressure and temperature, P1 250 psi, T1 700 degree Fahrenheit. If we go to table A6E for water with these characteristics, for water vapor with this characteristic, we can find its specific value and also its enthalpy. So we can find V1 and H1 from that table directly or by interpolation, but we can find it V1 and H1 for um, steam with these properties. Then, as I discussed earlier, to find mass flow rate, you can use this equation like previous example, and that equal to 1 divided by V1 specific volume, with velocity, and cross-section area. And which we have all of them. A1 we have 0.2 foot squared. V1 or actually velocity we don't have. And this one also the specific volume we have. Mass flow rate also is given. So we can use this equation actually to find velocity of the steam at the entrance of the nozzle. By restructuring, actually, we can write like this: m dot divided by a1 times specific value. So even by restructuring, we can find the velocity of the steam at the entrance of this nozzle. So we find the answer for part A of the question. In part B, we are interested to find the exit temperature of the steam from the nozzle. So we need to write the energy balance equation because we have a steady flow. Then, like previous example, this term, the E of system change in the energy of the system with time is 0. Then E dot in will be equal to E dot out, exactly similar to the previous example. Here is also like what we had for diffuser, m dot times h1 plus v1 power 2 divided by 2. M dot h1 is for flow energy and internal energy. And this was at the entrance. We have this. At the exit, actually the energy of the flow which come to the nozzle is this much, E in. And energy which the change the energy, this energy will be equal to the heat transfer portion or a fraction of the energy is transferred to the surrounding by heat transfer or thermal energy transfer to surrounding Q dot out, which we had in the question instruction as well. And also the other fraction is the energy of the flow at the exit of the nozzle. So and W dot 0 delta P is 0 as we discussed earlier. So we have this equation that H1 plus V1 power 2 divided 2 and so on. The difference here with the previous example is this Q dot out, which you should notice. And if we divide all of this equation to m dot, then we will have by substitution of the and restructuring of the equation, actually we will have this equation H2 will be equal to H1 minus Q out minus V2 power 2 minus V1 power 2 divided by 2, which is, you can guess this part is easy. And about H1 is this side, it's okay. About Q out, Q dot out divided by M dot will give us the Q out. Both of them are in terms of the rate actually. So Q out is the heat transfer per unit mass from the uh, flow in our control volume actually. So Q out. This is not rate of heat transfer. This is heat transfer actually uh, from control volume to surrounding in in term of unit mass. So we have this equation to find H2 or enthalpy of the working fluid or steam at the exit of our nozzle. By substitution of all of this information, we have H1 and we have Q, which is given in the question instruction. This is the as I discussed earlier, this is heat loss from the nozzle per unit mass. The Q, which we have here as well, is that one. Then by substitution of H1, Q out 1.2, and V2, we have calculated in previous part A. We have V1 as well, and V1 we have calculated. We have V2, and we substitute in this equation, and finally we can have this. We need also to use this unity conversion ratio. Then finally we have H2, which is enthalpy of the working fluid at the exit of the nozzle. So we have H2, enthalpy of the steam. Then we need to go to the table and find the temperature. The question actually here is we need to find the exit temperature. So we have enthalpy. We need to go to the table and find temperature for this enthalpy for steam. So the table which we can refer is table A6E for superheated water. How we know this is superheated water? As we discussed in previous chapter, to use this thermodynamics table for water especially, we need to determine in which region it is. And as we discussed earlier, we need to compare the properties which we have with the mixture actually. If mixture, saturated mixture. Here, the temperature and pressure which we have, if we compare them with the properties of the water in the table, which is for saturated water, we understand that what we have here is superheated water. Then we need to refer to the table for superheated water. For superheated water, which we have here, we have its pressure and also its enthalpy. The pressure is given, enthalpy we have calculated. So to find the temperature for this pressure and this enthalpy, we need to go to the table. The pressure is 200 psi, P is 200 psi, and the H is 0.4. So we need to come to this table for superheated water, table A6I, which is for an English unit. Actually, we have same table for the SI unit, as you know. So the pressure is 200 psi, is part of the table, and enthalpy is this row. Okay, so for this enthalpy 1300 is in this region actually is bigger than this, less than this. So it means should be between these two. and the temperature for these two are 7 and 600. So what we have here is temperature, enthalpy. So temperature we have are 600, this we don't know, and 700, and enthalpy which we have here is 32.3. Our enthalpy and enthalpy for this temperature. Again, by this information and interpolation, simply we can find T, which T by interpolation which we find, or T2, will be equal to 662.0 degree Fahrenheit. So simply by doing this interpolation, we can find the temperature of the steam at the exit of the nozzle, and which is equal to 6 degree Fahrenheit.